Do we have seminar again next week?
Ah. Well, wait, is next week reading week?
That's next Thursday is reading day. You're on.
Okay. Cool. I'm gonna go over here.
Hello. Hey everyone, let's get started. Okay, our first speaker today is Roy Bell. Roy is from Peoria, Illinois, and he received a Bachelor of Science in Electrical Engineering from the University of Illinois in 2008. And he's been involved in several research projects, including global maximum power point tracking of conventional PV systems, distributed generation control of micropower systems, and passivity-based synchronization of microgrid connected power inverters. Currently, he's pursuing a master's degree under Professor Robert Palawa and researching the application of differential power processing to PV systems.
Thanks. Well, thank you. All right, so today I'm going to be talking about something I've been working on since last fall. It's an alternative differential power processing architecture for the application of photovoltaic systems. Shiben has been working on something that's called PV to PV, differential power processing. I'm working on something that's slightly different. It's called PV to virtual bus differential power processing. So in order to, can we get rid of that thing? The top thing? Oh, it doesn't? Okay.
On the far left. Here at the far right with a little bump jack in. And move the mouse. Make it horizontal and then move the mouse.
Oh, then I think you got to move it away.
Just move your mouse.
Okay, great. Right. So in order to sort of motivate the discussion of this topology that I've been working on, I want to talk about something that I think the majority of you are familiar with, which is just the implementation of using bypass diodes. That's just a conventional PV system. And then kind of just segue from there into the topology that I've been working on and talk about power flow in that system, and then talk about power flow in the system that Shiben, as well as a few others, have been working on, which is the PV to PV topology. And then from there, just sort of talk about some of the maximum power point tracking algorithms that have been implemented for differential power processing in the realm of that topology, the PV to PV topology. And then talk about, from there, just talk about some of the work that I've been doing for trying to implement maximum power point tracking on my topology. I mentioned in the abstract that I was going to talk about some of the simulation results I got, but I think that I wasn't really comfortable with presenting the mathematics behind that because it's still not really complete. So I'm really just going to sort of end it right at what I'm working on right now, which is sort of further polishing up the mathematics behind that. Okay, that's fine. So I want to start off with a few definitions. So when I say PV module, I mean that it's essentially a PV panel, like a lot of you are familiar with that term. It's interchangeable with PV module. And a module is typically composed of 3 to 4 submodules, where each submodule has a specific amount of series connected cells in the submodule. And each of these submodules are accessible through the junction box on a PV panel. And that's typically where the bypass diodes are connected. And that's where the power electronics will be connected when I talk about the topology that I've been working on. And if you want to know why you want to do maximum power point tracking at the submodule level, just ask at the end of the presentation, and I'll let you know why that's beneficial. So why do we series connect submodules, or why do we series connect modules? An obvious reason is because it increases the insulation capacity of the system. It increases the power out of the system, right? You increase voltage, you increase the power out of the system. But another reason why you do that is because the losses of the IGBTs in the central inverter are a stronger function of the current that's through them. So rather than increasing the capacity through increasing the string current, you would it'd be more beneficial to increase the voltage because you don't have as many losses in that central inverter. And also, going from an IGBT that's rated for several hundred volts to an IGBT that's rated for 1,000 or 1,000 volts, the increase in cost and size is marginal. So you have that other benefit as well. So that's a reason why you series connect modules. But that comes with a caveat. And that is because all of these submodules are series connected, so they share the same current. And that current is set by the string current. And this isn't a problem if you don't have mismatch between submodules, because all of the IV characteristic curves are the same. So that means that all of the maximum power point currents are the same. So you can just set the string current to the maximum power point current and sort of just perturb and observe around that point, and then everyone's happy. You can go home, hug your family, do whatever you want. Everything's perfect. But that's not the way it works in the real world. There's always going to be some hiccups, and in this case, you have mismatch. So what do I mean by mismatch? I just mean that you have variation in the maximum power point current between the IV curves of each submodule. So say you have a mismatch in the first submodule. So if you wanted to extract all of the power out of the maximum amount of power for each submodule, you couldn't. There doesn't exist a submodule, or there doesn't exist a string current that does that, right? And you can see just by how that line works. So if you set I string to be the maximum power point current of the submodule 1, you would be operating submodule 1 at its maximum power point, but you'd be operating the other submodules at like half of their maximum power point. And likewise, if you set the string current equal to the higher vertical or the horizontal bar, which corresponds to the maximum power point currents of all of the other submodules, you'd be operating those at their maximum power points, but you would also be operating submodule 1 in the second quadrant, and it would start dissipating power, right? And that's why we use bypass diodes. Bypass diodes prevent that from happening, because as soon as the string current exceeds the short circuit current of, say, submodule 1, the diode turns on because the voltage across it is 0. So then that diode starts to compensate for the excess amount of string current that is going through that submodule, right? So in a way, these diodes are essentially compensating for the mismatch, but they're not operating the submodule at its maximum power point, right? It's just sort of shedding that extra amount of current away from that submodule and keeping it within the first quadrant. And also, you're not operating that submodule at its maximum power point, right? You're shorting it out. So if you kind of use and the way the current through the diode, how that varies, that depends on the KCL that's I wrote above, and that depends on the short circuit current and the string current. So the higher the string current, the higher the diode current by that KCL. And the reason that KCL works out is because if you take the string current, say at the rightmost node, you can see that equals the current through the diode and the submodule. And if you go back to the other node, you can see that the string current is kind of between each one of these points, right? Just by KCL. So if you use that kind of intuition, you can use that to sort of compensate for the mismatch current. If you can somehow implement some kind of current source to compensate for the mismatch. So say you have the same mismatch for submodule 1. If you can somehow construct a current source that can provide for that mismatch between some set string current and that submodule's maximum power point current, then you can operate that submodule at its maximum power point. And likewise, same thing for submodule 2. So say that maximum power point current is higher than the string current, you should be able to use a current source that can provide for that mismatch as well. And that means that these current sources should be bidirectional. They should be able to absorb and inject current, right? So where's that current coming from, though? That current is really coming from the submodules, because those are the things that are generating power. So it's not like it's coming from the central inverter. That's just acting kind of like as a load, you know. And right, so because it's bidirectional and because it's coming from the submodule, I think it's more illustrative to sort of flip the direction of these current sources to just be like that. So, and the only thing that really does is that changes the KCL. So now it's the string current is equal to the submodule current minus this differential current, right? So how do we construct these current sources? The way you go about doing that is just by using a DC to DC converter, because a DC to DC converter can regulate current, right, for some voltage range. So that's characteristic of a current source, right? But you have these open secondary ports, and that means that you can't have power flow between submodules. So the way you go about dealing with that is you can either connect these ports to the entire string, or you can connect them together. If you connect them to the entire string to sort of get that compensated power, then that works, but the components of your secondary and your DC to DC converter need to be rated for that really large voltage. So you have to use like really large voltage rated switches, and that limits your switching frequency of your DC to DC converter, and that increases generally that increases the size of your magnetic component that you use in your DC to DC converter, right? So instead, in order to sort of maintain modularity and maintain the ability to use like small power electronics, you would just connect them all together, and then you can make that that bus voltage equal to whatever you want it to be. And also, the reason why we use isolated DC to DC converters is because if you were to use a non-isolated DC to DC converter, then you would have this potential and this potential shorted together, and that would short out all the submodules like follows. All right. So this topology is called the PV to virtual bus differential power processing topology, and it's called virtual bus because essentially all of the submodules are virtual neighbors to each other. So if you need to inject power or current from a strongly performing submodule to a weakly performing submodule, it does so through the bus. It goes just like that. Say if submodule 2 was a weakly performing submodule, and submodule 1 and everything else was the same illumination, and they were producing the same amount of power, all of that power, this submodule would need to be compensated, so all of that power would come from the strongly performing submodules through the bus, and then it would be injected into submodule 2 to compensate and get it to operate at its maximum power point. And this sort of illustrates that. So say submodule, for 100 submodule connection, submodule 50 is mismatched. You would need to inject all of the strongly performing submodules that are the same illumination, same power generating type submodules. They would need to inject power through the bus, and then DPP50 would need to absorb that power to operate at its maximum power point. And you would need to bring down I string a little bit. So if I string were equal to the maximum power point of submodules, so for all the submodules except for submodule 50, then you would have the mismatch current I delta 1 would be 0, I delta 2 would be 0, and so on. And then you wouldn't be able to inject power onto the bus to have DPP50 absorb that power to operate at its maximum power point. So what you do is you lower the string current a little bit, and then that allows the DPPs to inject more current onto the bus, and then that allows DPP50 to compensate for the mismatch. So for the case when you have a maximum power, like when the submodule's maximum power is about 75 watts, this sort of shows like the distribution and the power process. The lower plot shows the distribution and the power process for all of these converters. And all of these like small arrows, all of these small green arrows correspond to this small amount of power processed in the plot, besides converter 50, which corresponds to these big red arrows. and that just shows that like all of the evenly illuminated submodules are injecting a small amount of power onto the bus, and all of this small amount of power accumulates and is injected back to submodule 50 to compensate for it and operate it at its maximum power point. And this is for a 5% mismatch case. So that amount of power is the aggregate amount of power that's processed is pretty small for this topology, and that is something that I will take advantage of when I start talking about maximum power point tracking. So for this case, when you have, say, 10% mismatch for one panel, you end up processing about 15 watts. And that's 15 watts compared to, say, this is a 100 submodule system. That's about 7.5 kilowatt system. That's practically negligible. So when you start looking at how you should spec your converters with respect to efficiency, you can get away with using inefficient converters because you're processing so little amount of power that the total power lost is like negligible compared to the total power from the system, right? So that's something to remember, is you can get away with using inefficient converters for this topology. So to compare that to the PV to PV architecture, which is essentially just another differential power processing architecture that compensates for mismatch in a slightly different way. When you have the same kind of mismatch from the scenario I showed before, the aggregate amount of power processed is like way bigger, and that's because of how everything is coupled in this topology. And I won't go into the details about that unless you want me to at the end. But the takeaway from this is that the total amount of power that you process is quite a bit. So for the PV to virtual bus topology, when you have 10% mismatch, you were processing about 15 watts. When you have 10% mismatch here, you process about 180 watts. So you can't get away with using inefficient converters in this topology. They have to be pretty efficient, and we haven't quantified that yet, but the point is that you can't really get away with using inefficient converters here. So that means that you can't. It's not good. It wouldn't be a good idea to sense current locally for these DPPs, because you would either have to do like some sort of lossless current sensing, which is good, but I mean it just hasn't been done yet, or you'd have to like put a series, like a sense resistor in the DPP and sense current that way, and that would lower your converter efficiency, which is not a good idea for this topology. So you have to rely on something else. And what's been implemented in the past is that you just try to maximize the string voltage, or you try to maximize the submodule voltage locally, and that's been shown to work. But some problems that have come out of that are that in order for the convergence speed to be sufficiently fast, you have to increase the lines of communications between DPPs. You increase redundancy to increase the convergence speed, and also the perturbation coupling leads to increased tracking error. So when one DPP perturbs, its power processed changes, and that has to go and come from somewhere, and that affects all of the DPP, all of the power processed by all the other DPPs in the string because it's tightly coupled, and that in effect affects the states of all of the submodules in the string. So when you affect the states of all the submodules in the string for a particular, for say DPP1 perturbs, then you can't, it affects your maximum power point tracking algorithm of all the other DPPs above it. So that leads to tracking error. So some goals for this maximum power point tracking algorithm for this topology is that we want, like the maximum power point tracking algorithm that's been developed for the PV to PV topology, we want it to be distributed, but at the same time we want it to be asynchronous. And for the previous topology, they sort of got around the coupling problem by synchronizing the perturbations, but that requires extra lines of communication and increases like system level cost or whatever you want to call it. So something that would be good to do is to sort of take away those extra lines of communication by implementing some asynchronous maximum power point tracking algorithm. And by asynchronous, I just mean that all of these DPPs are perturbing and observing independently from each other. They're not perturbing and observing at the same time. And one of the ways that I'm going to show that you can do that, so you can take advantage of the relaxed efficiency requirement for the DPPs, and you can sense current locally, and I'll show why that's beneficial in a second. And also, I'll show how I'm going to address the perturbation coupling problem too. So if you can get away with using inefficient converters, you can implement converters that sense current locally, and if somehow you had access to the string current, you can calculate the submodule current, and a way you can have access to the string current is through the bus. So the bus can be at any potential that you want it to be. So if you have the bus at the same potential as the central inverter, then they can communicate with each other without any sort of extra hardware. But I mean, you still need some lines of communication, but whatever. So like, you can communicate to the string current through the bus to the DPPs, and then they'd have the string current. They'd have their local process current, so they can calculate their submodule current. And then from there, you can sense each of the submodule voltages locally and losslessly, and you can do a direct calculation on the submodule power. So then you can do perform a distributed maximum power point tracking algorithm that runs a perturb and observe locally on a DPP, a submodule's power, right? But you still have coupling, because as soon as even if you're trying to track, say, submodule 1's maximum power point, whenever it perturbs, it's going to either inject or absorb power from the bus, and that's going to affect the states of all of the submodules above it. So when they're trying to do their thing, perform maximum power point tracking, it's going to affect their algorithms. So that's something that I'm working on right now. Is I'm trying to further develop the mathematics behind the coupling that I just mentioned, and I'm working on the mathematics behind the maximum power point tracking. But it's essentially done. But I just want to polish it up a little bit more before I present it. And I also need to develop appropriate hardware for this implementation. And basically, the hardware would just need microcontrollers that have hardware multipliers, so I can do that power calculation. So that's where I'm at right now. Any questions? No? Oh man, that's not a good sign. Oh well. No questions at all? Okay. Huh?
I guess you need like fewer communication lines, right?
Yeah.
It seems like you need some extra like power conduction pads, right?
Wait, what do you mean?
Like relative to the one in which the DPPs are sort of in between two modules or submodules, you have like a whole parallel path for energy to flow, right? So
Yeah.
So I mean, you get away from like with less communication, but you need more conductors, right?
You need more conductors.
So you go to like
This.
Yeah.
Mm-hmm.
Don't you need like relative to the other topology? Don't you need like your paths for current to go from your DPPs to this?
Yeah, that's true, and I mean that's a drawback for this topology. If you want to like pull out like so each of these DPPs, I mean they're all power converters, so they have input and output capacitors. And I should have said that I was just showing this bus capacitance explicitly, and that's basically just represents the aggregate of all of the output capacitors. And yeah, so like all of these DPPs need to be connected to that bus somehow, and it's through it's through conductors. And that's a drawback for this topology, is that you need, I guess, extra conducting cables for that. But yeah.
So you have to have one string. Do they have to all be on the same like they call it vector bus?
It's like, yeah, it's a virtual bus. Yeah.
They have to all be on the same virtual bus, or could you like break it in half?
Yeah, you could. I haven't looked into that. I think Pradeep had some work in his thesis on like hybrid topologies, right? So like you like sort of use like a PV to PV PV to bus type thing, and you can break up the buses and then do like PV to PV in between or something. But yeah, you can do that. Yeah.
Just see, like, if you can arbitrarily choose how many devices are connected to your virtual bus, more or less.
I think so. Yeah.
There's probably some limit on it.
Yeah. Yeah. I mean, like the limit on, I guess, to sort of build on that, the limit on how many, say, submodules that you have is the isolation voltage for the transformer that you use in your DC to DC converter. Because as soon as you exceed that, then you exceed insulation limits for the transformer that you use, and yeah. But yeah, there are limitations for this topology for sure. Yeah. Any other questions? No? Okay, thank you. There you go.
Our second speaker today is Madi
Madi.
Zholbaryssov. He is from Kazakhstan, and he studied his undergrad at UIUC and graduated in December of 2011. His advisor is Professor Alejandro Dominguez Garcia, and he's planning to pursue a PhD in, what are you working on?
Yeah, I don't know yet.
He doesn't know yet, but he'll find a topic.
Okay, so I'm glad to see you all. So let me get started. So here's the outline of my presentation. And in my introduction, I will formulate a problem that I was trying to solve and explain its significance. So the growing demand for energy puts a lot of stress on power grid, which heavily depends on reliable operation of power converters. And operation close to design limits and increased requirements on efficiency make them vulnerable to different failures, which are typically characterized by changes in system dynamics, system components. In response to these concerns, tighter safety and reliability specifications have been imposed, which has resulted in increased activity on research with fault diagnosis technology. It is an issue of primary significance since it provides a reliable operation, safety, fault tolerance of dynamical systems, also automation of maintenance procedures, minimization of maintenance activities and costs, and enhancement of system performance through the early detection of component degradation, isolation and identification of multiple component failures, and system reconfiguration of a particular failure. It's attracting a lot of attention in a wide range of system engineering applications, including power plants, power grid, aircrafts, chemical processes, bioengineering systems. The main steps in fault diagnosis can be broken up into 3 steps. The first one is detection, which deals with determining if a malfunction has occurred in the system. Isolation considers the problem of identifying a failure, and accommodation, which attempts to correct a bad effect of failure. And any fault diagnostic system may include some or all of the above tasks. And in our work, we're interested in the first 2 tasks. And during past decades, intensely conducted research on fault diagnosis technology has yielded important algorithms, which are based on 2 types of approaches. Hardware redundancy approach, which is corresponds to constructing additional physical subsystems into a target system. And additional space size of the hardware makes this approach less attractive. And the appeal of the analytically dense approach lies in the fact that using information processing techniques, we can achieve more efficient, smaller size hardware. And this approach can be further broken up into two types: model-based, when an accurate model of the system is given, and model-free, when a system is mostly unknown and incoming data are processed using signal processing techniques or artificial intelligence. Model-based approaches, they often use observers or parameter estimation from the control theory, and most of them have been developed for linear time invariant systems, but power electronics, power converters pose implementation constraints for these algorithms. And in our work, we extend one of those approaches developed for LTI systems to switch linear systems, to which most power electronic systems belong. And we, for practical application, we will apply our approach to a photovoltaic system with differential power processing converters. And our goal is to detect and isolate faults in the components of DPP converters. Here I will present main ideas of an observer-based approach. So we model faults as additive disturbance inputs to the state space model. And suppose consider an observable LTI system with the fault disturbance, and each fault is described in terms of fault signature, which is vector space orientation of the fault, and fault magnitude function. With the single observer, we can detect this fault disturbance. We can construct an observer, and its error signal will converge to 0 when there is no fault, given our state estimator matrix, which is A minus LC, has stable eigenvalues. And when there is a fault disturbance, the residual generator will align with the fault signature mu. But if we have more than one fault in our system, then we can no longer distinguish them. And in this scenario, we need two residual generators, and such that each residual generator responds to exactly one type of fault and stay insensitive to another fault disturbance. And for example, here the fault psi should show up in R, but should not show up in gamma, and vice versa for fault disturbance phi. And mathematically, we can write these conditions to isolate these two faults in a straightforward way. So basically, the image of the fault signature mu should lie in the unobservable subspace of the first residual generator, but should not intersect its unobservable subspace of its corresponding residual generator, which is second line here. So our problem is to compute output injection matrices and output injection matrix L and the output matrices H mu and H nu. But instead of direct computation, we will construct a reduced order observer and residual generator for each fault using projection matrices, which are based on, it's called unobservability subspaces, which are computed using only A and C matrices and fault signatures mu and nu. And those unobservability subspaces, they satisfy 4 fundamental properties. The first 3 properties we can recognize. They ensure that each fault disturbance shows up in its corresponding residual generator, but does not show up in the second one. And the last property ensures that under closed-loop dynamics, unobservability subspaces stay invariant, which is important for the design of a reduced order observer. And this last property in geometric control theory is called AC invariance. And S mu and S nu unobservability subspaces are called AC invariant subspaces. And basically, in our example with 2 fault disturbances, we use projection matrices and project the original state space into subspaces. And for each subspace, we design reduced order observer and residual generator such that each of them will see exactly one type of fault and will not see any other types of faults. And basically, these matrices in our observer and residual generator are computed based on a subspace S mu and its projection matrix P, which is unique to fault signature mu. And in the next part of my presentation, I will tailor these ideas to switch linear case. And like consider a switch linear system, which is a family of linear individual subsystems with multiple fault disturbances. And general structure of an observer and a residual generator is similar to what we have to linear case. The problem here is because of the switching matrices A and B, our observer matrices also switch. And this causes one big problem, the switching phenomena in the unobservability subspace. When the unobservability subspace switch, we don't know how to construct a reduced order observer for that subspace. And so we need to look at this problem more, and we derived a condition which must be satisfied in order to avoid this switching phenomena and implement our fault detection and isolation filter for switch linear systems. And this necessary condition is not difficult to derive. Basically, the matrix A sigma epsilon, where epsilon is matrix which is computed recursively by the algorithm which is described in the earlier paper on geometric control. And the A sigma epsilon should not switch if we would like to implement our filter. And this condition allows us to implement an FDI filter for switch linear systems, choose a non-switching matrix F, and assign stable eigenvalues to ensure the stable operation of the filter and ensure the fast convergence of its residual signals. Any questions? Yeah, so here's the state space model of DPP converters, and this is in this PV system we have 3 submodules and 2 DP converters. This is a 5th order system with 4 modes determined by a switching signal sigma. And if we apply our necessary and sufficient condition for feasibility of an FDI filter, we can draw following conclusions. So for our PV system with 2D peak converters, we can design our filter if we measure all states. And when less measurements are made, then one of the two things happen. Either our A sigma epsilon matrix switches, which violates the invariance property of the subspaces for which we construct reduced order observer, or some states become unobservable, which implies that some faults are not detectable. And here I have included fault disturbances corresponding to inductors and capacitors. And fault signatures are derived using elementary analysis. And in the last part of my presentation, I will present some simulation results. Suppose a fault occurred in the inductor. In this example, I just decreased the inductance of the inductor at time 200 microseconds. And as a result, our simulations show that a residual generator, which corresponds to L1 inductor, becomes non-zero. And other residuals stay at zero, which shows that no other fault occurred in the system. And we were able to isolate the fault happening in the inductor L1. And when we add the capacitor fault at time 225 microseconds, its corresponding residual oscillates, which is a good sign, and residuals for other faults do not respond to that fault. Yeah. So in this example, we were able to isolate inductor and capacitor faults using our fault detection filter. So this is these two examples are very simple examples. We can make more complicated faults, and it's fine as long as we can describe them in terms of the fault disturbance in our state space model equations. And in conclusion, I would like to restate the main results. An FDI filter was extended and applied to switch linear systems. And if certain condition is satisfied, then we can implement our FDI filter. We can arbitrarily assign any eigenvalues, any stable eigenvalues for our state estimator matrices and guarantee the stable operation of the filter and fast convergence. And faults can be detected and isolated as soon as they occur, and it might help us to start the next task, accommodation task, to avoid a possible bad effect, but it's out of scope of this work. Thank you for your attention. Yeah. So here's the main references for our work. Yeah.
I have a question. So when you're detecting faults,
Yeah.
I mean, usually you assume that only one fault happens at a time, because
Yeah.
the probability of
Yeah.
the two faults happening at the exact same instant.
No, we're not talking about faults happening at the same instant.
Okay.
Different instance. So one fault occurred like at 200 microseconds, and then another fault occurred at later time. And then we are able to distinguish these faults.
Okay.
Yeah.
Yeah.
Yeah, this is like simple demonstration of the algorithm.
If they happen at the same time, can you distinguish? I mean,
Yeah,
separate?
yeah, you can. So the Josiah, he's meaning that no two faults can occur at the same time, like low zero probability. So. Yeah, any other questions? Yeah. I think it was a little bit complicated.